So, all right, our last chapter, chapter 11, remember there are 2 questions. So we'll have questions 7 and 8. Our chapter 11 did rely heavily on partial fraction decomposition because we only took one section from chapter 11, which was on partial fraction decomposition. And one of the things that we had to determine in using partial fraction decomposition is that we had to determine whether or not our rational expression was proper or improper. And it had to be proper. So if it's proper, then we use partial fraction decomposition. If not, then we don't. So now we're going to, for number 7, tell whether or not the given polynomial is proper or improper. If it is improper, we're going to write it as the sum of a polynomial and a proper rational expression, which we'll go over how to do that. So the expression that we're given here, the rational expression we're given is 9x cubed plus 5 divided by 9x cubed minus 64. So a rational expression is proper if the degree of the numerator is less than the degree of the denominator, the degree being the highest exponent on your variable. So in this case, our variable is x, our highest exponent is 3, x to the power of 3 is in the numerator and the denominator. So that means that our rational expression has the same degree in the numerator and the denominator. The same means it is improper. Proper rational expressions have to have numerators with degrees less than the degree of the denominator. Has to be less than, not less than or equal to. So if they're equal, it's improper, which means that this is improper. So we can go ahead and write that up. So we can say this rational expression is improper, since the degree of the numerator is equal to the degree of the denominator. This means that we need to rewrite it as the sum of a polynomial and a proper rational expression. So in order to rewrite this as the sum of a polynomial and a rational expression, we're going to go ahead and use long division. So just a quick reminder, when using long division, your numerator is your divisor and your denominator is the dividend. So your divisor or your numerator is the one that's going to be dividing 9x cubed minus 64. So when we write this out, we'll write 9x squared plus 5 is our divisor, so it's outside of our division bar. And inside we have 9x cubed minus 64. And whatever answer we get on top of our division bar, remember, is the quotient. Oh, this is squared. There we go. So we can go ahead and use long division here. Now, when we use long division, especially with polynomials, the best way to do it is to pick the first value in each case, divide them by each other and find what the value is and then multiply it. So in this case, we have 9x cubed plus 5, which is dividing 9x cubed minus 64. So our first terms in the dividend and the divisor is going to be 9x cubed. 9x cubed divided by 9x cubed is just 1. So the first value of our quotient is 1. And now we multiply 1 by 9x cubed plus 5, and we subtract that product. So we have minus 9x cubed plus 5. 9x cubed and 9x cubed cancel each other out because you're subtracting. You want to get rid of them. And what we're ending up left with is negative 64 minus 5. And this ends up giving us a negative 69. The negative 69 in this case is the remainder. And remember, when you're writing out your quotient, your answer is going to be the polynomial plus the remainder divided by the divisor. So the remainder is negative 69 divided by the divisor, which was 9x cubed plus 5. And this is our quotient. So then we can say our quotient is 1 plus negative 69 divided by 9x cubed plus 5, where 1 is considered the polynomial. And negative 69 divided by 9x cubed plus 5 is the proper rational expression. Thus, we have that 9x cubed plus 5 divided by 9x cubed plus 64 is equal to 1 plus negative 69. You can also write minus. It asks us to write the sum, so that's why we're writing plus negative. Plus negative 69 over 9x cubed plus 5. So when encountering a problem like this, it's really just asking you to do long division and rewrite your improper fraction as a polynomial plus a rational expression. And finally, our last problem, problem 8, we want to find the partial fraction decomposition of x squared minus 6x plus 2. So of course we're going to do a partial fraction decomposition problem since it was mostly chapter 11.5. So we can go ahead and solve this. One quick thing, because we always just want to make sure that the expression that we're given is a proper fraction, not an improper fraction. We just want to make sure that the degree of the numerator is less than the degree of the denominator. So in this case, the degree of our numerator is x squared. The degree of our denominator, since we do have x squared plus 9 squared, the highest degree of our denominator is technically going to be 4, which means that we're safe and this is a proper rational expression. So we're good to go ahead and take the partial fraction decomposition. The next thing that we want to do in this case is we want to determine the case in which we're going to use. Because remember, there were 4 cases with finding partial fraction decompositions. We want to identify what case it was. Because if we remember, it was our non-repeated factor, then it was our repeated factors, and then it was our irreducible, our non-repeated irreducible quadratic factor, and then our repeated irreducible quadratic factor. So determining our case is what's going to tell us what equation that we're going to end up using. So if we look at our problem here, we have x squared minus 6x plus 2 divided by x squared plus 9, which is squared. So in this case, x squared plus 9 is irreducible. We also see that it's squared, which means it's technically the same thing as saying x squared plus 9 times x squared plus 9. So it's going to be repeated. This means that our denominator is a repeated irreducible quadratic factor. So we use the form in case 4. So from case 4, we get the form x squared minus 6x plus 2 divided by x squared plus 9 squared is going to be expressed as ax plus b divided by x squared plus 9, not squared, plus cx plus d divided by x squared plus 9 squared. So this is the form that we have to use that was given to us in case 4, determined by our denominator. So now we can go ahead and start our partial fraction decomposition. So one of the first things that we want to do is we want to clear out the denominators, which also means to clear the fractions. So to clear the fractions, we need to multiply each term by x squared plus 9 squared. This will get rid of each one of our denominators. It will also end up making us multiply ax plus b by x squared plus 9, but we can easily do that as long as we don't have to deal with fractions or irrational expressions with denominators. So we multiply each term by x squared plus 9 squared. In order to get just our numerator now, x squared minus 6x plus 2. Let's go ahead and give ourselves some more room, kind of squished here, which is equal to ax plus b times x squared plus 9 plus cx plus d. And now we just want to simplify expand. So we want to expand as much as possible, and then we're going to collect our terms. So when we expand, we'll move this up a little bit. We're just multiplying ax plus b and x squared plus 9 at this point. So when we multiply these together, we'll end up with an ax cubed plus 9ax plus bx squared plus 9b. Then we have our plus cx plus d. So in this case, we just expanded. Now we want to collect our terms and group them together. And all of this is still just going on the right-hand side of our equation. We're not doing anything with the left-hand side. So collecting our terms together, ax cubed is a single term, same with bx squared, but we have two x terms, so we'll group them to say 9a plus c times x. And our single constant terms we have as well. So we'll group those to get 9b plus d. And here we collected and grouped terms. So we collected and grouped our terms together. And we did this so that now we can equate the coefficients of like powers of x to get our system of equations. So we have four different terms. We have x cubed, x squared, x, and constants, or x to the power of 0. So now we're going to equate each one of these. So our first value, which is a is going to be 0. A is 0. Since there is no x cubed term on our left-hand side. That means that it's the same thing as saying 0x cubed. So if ax cubed is equal to 0x cubed, that means a is 0. So we say since ax cubed is equal to 0x cubed. Then we get that b is equal to 1. And this is because bx squared is equal to 1x squared. And now a little bit more tricky. We have negative 6x has to be equal to 9a plus c times x. So we get negative 6 is equal to 9a plus c. And we get that this is because 9a plus c times x has to be equal to negative 6x for this equation to hold. Then lastly, a positive 2 has to be equal to 9b plus d. Since 9b plus d is equal to 2. So we have equations for a and b, but we don't have, or we have values of a and b, but we don't have values of c or d. So we have to use these latter two equations to solve for c and d. So solving for c and d, we have 9a plus c is equal to negative 6, where we know that a is equal to 0. So it's really just 9 times 0 plus c is equal to negative 6. So we have that c is equal to negative 6. Then for d, we have 9b plus d is equal to 2, where b is equal to 1, so we have 9 times 1 plus d is equal to 2. So that's 9 plus d is equal to 2. 2 minus 9 is going to be negative 7. So d is equal to negative 7. And there we have it. We've solved for our values of a, b, c, and d, which are not our final answers. So let's highlight that in blue instead of yellow. C, there we go. So we found the values of a, b, c, and d, but remember now we want to plug this into our equation in the form of ax plus b divided by x squared plus 9 plus cx plus d divided by x squared plus 9 squared. So using a is equal to 0, b is equal to 1, c is equal to negative 6, and d is equal to negative 7, we have that x squared minus 6x plus 2 divided by x squared plus 9 squared is going to be equal to 0x plus 1 divided by x squared plus 9 plus negative 6x minus 7 divided by x squared plus 9 all squared. So lastly, just simplifying here, we get x squared minus 6x plus 2 divided by x squared plus 9 squared is equal to 1 over x squared plus 9 plus negative 6x minus 7 divided by x squared plus 9 squared. And that would be our final answer for our partial fraction decomposition. Oof. So definitely a long problem there. So if we remember from going over partial fraction decomposition in our lecture video, there are other ways to solve for the values of A, B, C, D, etc. For this problem specifically, this was the easiest way to solve for the values, but you could also try canceling out values by plugging in very specific values of x and then solving. For this specific equation that we had to solve for the partial fraction decomposition of, using this method worked easier, but remember that in other problems with most of the time along with case 1 and case 2, using that formula for just picking specific values of x to get rid of specific values A, B, C, D, etc. can be easier. So go back and watch that video if you want to review those techniques a little bit better. So all right, that wraps up our final exam review. So thank you all for a great summer class and good luck with the final exam. Reminder, if there are any questions or concerns before the end of our course time, you can always send me an email. So all right, good luck studying everyone and have a great rest of your summer.